So let's start our class. Okay, so we are already in question where we have to start the class. So then voice test is done. I hope my voice is clear, audible. Okay, there is some disturbance at my voice. I don't know whether let me. I don't know if that's been catched into our guys. So I'm just launching the technical check. Please let me know if my voice is audible clearly or if I want to increase my voice or anything like that. Also, please let me know if my this board is clear. So yeah, waiting for others. Yeah, yeah, okay, cool. So waiting for more students to arrive, guys. Come on, please be here. Okay. So yeah, I had Prasad Delhi. So I'm doing good. So how are you? Okay, so then I'm going to for yeah, actually there are very best students. Any issues? If there's any issues, pretty recap program also. Any another program schedule today? Any of sorry, any of the Navodas? Okay, I think right. So, did you have any class before this? Like yes, I think there was math class. But the strength of students is very low. I mean, okay, so waiting for more students to arrive here. Yes, so my voice is clear and my screen is visible clearly. So let's begin our class. So in today's class, we'll be starting with electromagnetic induction. Okay. So what is it? So before we go to this, I want to give a few detail. I mean, I want to introduce. I want to give a quick recap of previous chapters. Like yeah. So we are not considering. I mean, we are not connecting the two chapters: electric effects of magnetic effects of electric current and the magnetism and matter. So these two chapters are having very less weightage in your day needs. So we are skipping these two chapters for now. So if any of the students require it later in later sections, so in later classes, once we complete all the chapters which we have targeted to complete. So we have targeted to complete all high weightage chapters first. So which have very good, I mean, which carry good marks. So at least minimum of we get at least minimum of one or two questions in each chapter. So those chapters we are targeting first to complete. Then we'll be starting with the chapters which we are left on. Okay. So I hope everyone have started the registration process for JEE Mains. I think the application forms are being active since 16th of December. Hope everyone have started applying for JEE Mains. Okay, so let's quickly begin. Yeah. If you have any doubts regarding JEE Mains, you can contact any of our teachers or me too. And whenever if you have any doubts at any point, you would contact us. Okay, guys. That was one quick notification. Yeah. Coming to class, today we'll be starting with electromagnetic induction. Now, guys, yeah, let us have a brief introduction. So, say, tell me one thing. Say, if I have a charge which is stationary, so I want some few prerequisites to be known before we start. So, if a charge is stationary, what type of force can this stationary charge get? Or what are the fields? Or when I have a stationary charge which is in free space. What are the things which are possible to happen? Yes. I'm waiting for answers, guys. Come on, you could answer me. So I have a charge. Okay, I have a charge, and it's in a free space. What exists? The charge is not moving. The charge is at rest. Charge at rest. What type of field do I get? So we started with this, guys. Yeah, we started our 12th standard with this. So charges which are at rest. What type of electric? Okay, what type of field we get? We get yes, exactly, electric So when charges are at rest, we get electric field. Okay. So what happens when this charge is being applied with a force? Say I apply some force, maybe the magnetic force or maybe the electric force. Yes. So when I apply some force, this charge starts to move. Okay, with some velocity v. Say when I apply force, this charge starts to move with some velocity v. Now what is happening with this charge? What will this charge give? What will this charge give out? When this charge is stationary, we get electric field. When this charge starts to move, what happens? Correct, Madhavi. Come on, try to give answers, guys. Come on, students. Come on. There are many students here, and please try to give answers. So when a charge is stationary, it gives electric field. When a charge starts to move, what happens? Yes, correct, Madhavi. Others, please try to move. Please try to give answers. Priti, Chetan, Amit, Rakesh. Come on, guys. Please try to answer. What happens when the charge starts to move? So it just moves. What happens? What can charge move? Is it? Okay, cool. Correct, Madhavi. So a moving charge. So moving charge. Say a moving charge gives what? A moving charge gives both. Okay, it will give magnetic field. Yes. So moving charge produces magnetic field. Okay, when there is a charge, there is also presence of which field? When there is a charge, there is also presence of electric field also, right? Yes, correct, Bhargav. So what happens when the same charge, say if I have a charge, this accelerates. Okay, when the same charge starts to accelerate. So it continuously moves with a very rapid speed, very high speed. What happens to this charge or what will this charge give out? Come on, guys, I need answers. Okay, these are general questions, right? You could answer this easily. Chetan, Amit, Rakesh, Kriti. Yes, correct. Very good, Hariprasad. So yes, moving charges produce magnetic field and also electric field. Okay, since the charge itself gives electric field, so it gives electric field as well as magnetic field. But what happens when the charge accelerates? What happens when the charge accelerates? Yes, when the charge accelerates, it gives electromagnetic radiation, or it's also called as EM waves. So we have studied EM waves as a separate chapter in CBSE. Okay, guys, we have studied EM waves as a separate chapter in our CBSE class. So I think we also studied the Ampere's circuital law with this, right? So these were the few basics which we require. Now, guys, yes, when the charge is present in free space, and say I have some external electric field, or I keep this charge in the presence of external electric field, what happens? The next question is: I have a charge in the free space, and I have a charge in the presence of uniform electric field. What happens? Come on, guys, come on, please reply, answer. Guys, try to be active. Try to be active. Please be active, guys. So if you don't answer, like, yeah, it would be. Then you may also feel tend to be bored, and I may also tend to feel like, okay, yawning and stuff. So that should not happen, right? Let's talk. Okay. So we have a charge here, and this charge is under the influence of electric field. What happens? Come on, guys. Come on. Please try to answer. Guys, come on, give the answers. Yes, this charge will experience some force, right? What is that force given by? So this charge will experience some force. In which direction? In the direction of electric field, right? So this force is nothing but given by q times of electric field. Okay, right? Okay. Now, yes, charge experiences force and it's q times of E. So F is equal to q into E. Now, guys, I have a new situation for you. Instead of electric field, okay, this chapter is not done to you in Avanti, but it should have been done in your CBSE. So you have a charge now. This charge is being kept in uniform magnetic field. So now I have kept this charge not in the electric field, in a uniform magnetic field. Okay, what happens now? So I have kept this charge in a uniform magnetic field. What happens now? Yes, come on, Prakash. Hi, Prakash. Good evening. Priti, Chetan, Rakesh. Please try to answer, guys. Come on. Here, Hariprasad. I think Bhargav is here. Hariprasad is here, and Madhavi is here. Okay, there was Rekha Kumari. Hi. Yes, yes. So, what is the force with which? Yes, correct, Rakesh. Very good. Very good, Rakesh. Rakesh, but please also note that you have to, whenever you are giving the equation, you have to give the cos or sine component. Okay. Cool. So here we had uniform magnetic field now. Yes, in the presence of uniform magnetic field, what happens? Yes, my charge experiences a force is given by F is equals to Q into V cross B, or it's given as F is equals to Q into VB sine theta. Since I have not mentioned what is my theta here, we can't write QVB directly, okay? Or we can't write Q into V directly because I didn't give velocity also. Suppose if V is equals to 0, what happens? Suppose this charge is stationary and this is kept in a uniform magnetic field. What happens, guys? See, now this charge is stationary and is kept in a uniform magnetic field. What will happen? Yes, the force experienced. Yes, if velocity is equals to 0, then automatically my force will also be equals to 0. So a stationary charge will not experience any force. A stationary charge will not experience any force in the presence of uniform magnetic field. Okay. So I think by now you might have also learned this something called as what's that? I think you might have learned this. Have you learned this by now, guys? Again, this is in one of the chapters which is not being done, but this should have been known to you guys. Hi, Anisha, good evening. Yes. So, what is a cyclotron? What's a cyclotron? What happens in a cyclotron? What is a cyclotron and what happens in it? So, how many of you know Big Bang Theory? It's all started with the Big Bang. Okay, I'm not talking about the series, guys. Yes, so I'm talking about the Big Bang Theory, which is yet known as the origin of our universe, right? There was a big ball and a big red giant ball which exploded, and everything started. Like, yeah, yes. Good, yeah. That's theory. So the similarly, yeah, Stephen Hawking, because of Stephen Hawking in Switzerland, we had a huge cyclotron. I hope everyone knows that. Yes, exactly, Adi Prasad. Very good, Adi Prasad. Yes, correct, Rakesh. Cool, superb. So yeah, there was a very huge, very big cyclotron in Sweden. I think. Yes, Switzerland was Sweden. Yeah, yeah. There was this huge cyclotron built to check for a God particle. I hope many of you might not know. So there are some quarks, or there are some minute particles called quarks or quarks. So which are minute than the atoms inside the atoms of you might be knowing neutrino, antineutrino, etc. Which might have been you might have studied them in 10th or in your 12th if your atoms and nuclear chapter is done in 12th. You might have learned all this. So to study that, there exists something called as Higgs boson. Now, I think that was the recent research which was going. So there was something called as Higgs boson, so which was given by the Higgs and Jagdish Chandra Bose, which was invented, say, which was discovered several years ago, maybe nearly a century ago, nearly. So Higgs boson was discovered, and this how does Higgs boson or this Higgs boson was also called as the dot particles. So something like that was happening. So okay, why are we going here? No, I was talking about cyclotron. So there was a huge cyclotron, and they came up with that research. So, but what is a cyclotron? Okay, is my voice very low, guys? Guys, is my voice very low? So I'm getting notification from one of friend that my voice is very low. Please let me know if my voice is very low. Hope everyone is able to hear my voice clearly, and it's good. Good enough. Yes, good. Cool. Thank you, Risha. So cyclotron in yeah, in your previous chapter, which was done. So in cyclotron, there exists two types of forces. Say one is, say I have a north pole and a south pole, and this north pole and south pole is kept, I mean, perpendicular to two Ds. So there are two D-shaped conductors. Okay, there are two D-shaped conductors, and these D-shaped conductors is connected to a alternating source. Then what happens? We inject a small charged particle, say maybe a proton or an electron. Say I have, I'll just put a spark here, small spark here. What happens? The spark is nothing but some number of, no, Krishna, not that. Okay, cool. So yeah, there was a small spark kept here. So what happens because of the alternating force? So there exists some electric field between these two Ds, right? So there were few electric field existing. Say this was positively charged, this was negatively charged initially. So there was some electric field. So because of this electric field, this charge experiences a force F is equal to Q times of E. Then there exists a magnetic field perpendicular to this, exactly perpendicular to this. There exists a magnetic field. Yes, device used to accelerate positive charges or negative charges too. Okay. So device used to accelerate. Yes. So cyclotron is the device which is used to accelerate the charged particles. Okay. This is the stuff. So what happens? Yeah, there exists some magnetic field. Okay. There exists some magnetic fields which I'm drawing here perpendicular to that of the charge. So this charge experiences now two types of force. What are the two forces? So what are the two forces which are being existing here? So because of these two Ds, there exists an electric field E, and because of this permanent magnet or an electromagnet which is kept here perpendicular to this, there exists a magnetic field B, right? Yes. So what is the combination of these two forces called as, or what is the force experienced by this charge, the yellow dot which is present here? So what is it called as? Yeah, come on guys. I want you to guess that. Yes, exactly, Rakesh. Very good. So it's called as, yes. Others, I want more answers, guys. Come on. So the net force, then this charge experience is given by. So because what's happening? So we learned that the stationary charge, which is stationary, won't be affected by the magnetic field. But when it's in the presence of electric field, it tries to move, right? When it's in the presence of electric field, it tries to move with some velocity v. When it's moving, it should have some velocity v. So when it's moving, that moving charge will experience a force F is equal to Q to V cross V, or F is equal to Q V sin theta. So yeah, this we learned. This is what happening. This is what's happening in cyclotron, and this continuous changing of cycles and increase of electric field or increase of magnetic field or charge accelerates the charge, and the charge executes which type of path? Yes, the charge executes an helical path. Suppose if same electric field, same amount of electric field is applied, then the charge would execute a circular path, right? So this is how your Lorentz come in. Your cyclotron works. Yes, that force which it experiences is called as the Lorentz force. Okay, it was your Lorentz force. Okay. The Lorentz force is nothing but combination of your magnetic force, the force due to magnetic field experienced by the charge and force due to the electric field experienced by the charge, that is given by Lorentz force is equals to Q times of E plus Q times of V cross P. So this was what the Lorentz force is given by. So these were the few basic things which we wanted to know before we start this chapter. Okay. So yeah, we are going to start this new chapter. Anyway, guys, yeah, as the previous in yesterday's class, I was not able to come because there was some issue with my what to say. There was some issue with my device, so I couldn't turn on. So I was present in your class, but in as a host, co-host. That's it. Yeah. Cool, guys. Yeah. Um, cool. So we'll be starting with electromagnetic induction today. So what do you mean by induction, guys? We had learned that, right? So induction. What is induction? What do you call different? Can you give a synonym for induction? Induction ಅಂದ್ರೆ ಏನು ಅದಕ್ಕೊಂದು ಪರ್ಯಾಯ ಪದ. So I need synonym for induction. What do you mean by induction? So can we say something which is being done by forces, or something which is being done forcefully? Say in induction, we studied that a neutral wall was converted, was forced to become positively charged on one side and negatively charged on another side when a negatively charged balloon was brought near it. So this was the induction which we learned. So this is similarly here we are going to learn about the electromagnetic induction. So we are going to start with a new chapter, the electromagnetic induction. So we'll be learning about Faraday's laws of EMI, applications of EMI, and LR circuits in this entire chapter. Okay, cool. Okay, cool, guys. So let's come to our first experiment called as Oyster's experiment. How many of you remember Oyster's experiment from your 10th standard? Or maybe from your previous chapter also. So what is Oyster's experiment? Can anyone tell me? At least just give me the name. So maybe you might not know what is Oyster's experiment exactly by now. But if I tell, you will know. Yes, sir, I know this. So can you name? Can you say what is Oyster's experiment? What did Oyster do? So just name few components what he used. I'll get to know you have learned that Oyster's experiment. Come on, guys. So to do Oyster's experiment, what are the things we require? Okay, first, if you know, guys, if you know what Oyster's experiment is, click on S. Else click on no. So that way I can go fast, right? So come on, guys, please be responsive. Please respond. Yeah, very good, Hari Prasad, very good. I got it. Superb, guys. Okay. Okay, cool. I know. Yeah, yes. Super. Many of you know this. Cool. So yeah. So Oyster experiment is nothing but say, yeah, what did this guy do? So this guy took a conductor. Oyster took a conductor, and he passed some current through this conductor. Say maybe a DC current. Yes. So he passed some DC current. Say from now on, yeah, this is the direct current from the battery. He passed the direct current through this conductor. Then what did he do? He took a compass. So he took a magnetic compass, and the magnetic compass which was half red and half blue, right? So it had a magnet inside it. So he took this compass, and when this compass was held near this current carrying conductor, what happened? So when he took this magnetic compass near the conductor, what happened, guys? Come on. So when the current was flowing, the compass deflected, right? So if you remember, again, the compass deflected in such a way that it made a circular path. So from this, Oyster given theory, yes, compass showed deflection, correct radiation. So it showed deflection, and yeah, that deflection when it tested on different angles. So when it took the compass here, so it showed a deflection in such a way that there formed a circle. So this compass formed a circle. So Oyster, what did he do? Whenever a current carrying conductor is present, there exists a magnetic field which is circular in path. So looking at this, there was one more rule called as, how many of you know this rule? How many of you know this rule, guys? Come on. There was something called as right hand thumb rule or screw rule. Okay, it was also called as the screw rule. I think we discussed this, did we? Sometime. I think somewhere during your midterms, I think we discussed something similar to this. Yes, cool. So yeah, so when you hold a conductor, say when you hold a current carrying conductor in your right hand, say if you have a conductor now, if you hold it in your right hand, okay. Now the thumb, which is being shown, the thumb shows the direction of your current, right? And the finger sensor thing shows the direction of magnetic field. So from here, you got to know that yes, the fingers encircling shows the direction of magnetic field, and this encirclement shows that the magnetic field also circles. Okay, this magnetic field, this fingers encircling also shows that the magnetic field also encircles. Okay, this only is not the one. So I think in your 10th standard you might also have seen something like this. So there was okay, yeah. So there was a paper and a conductor passing through the middle of the paper, and there were few iron filings. When current was flowing through this conductor, what happened to these iron filings? So hope you remember this experiment also. There are few iron filings. Iron filings are those iron scrap in powdered form. Yes. When current was flowing through this conductor, what happened? The iron filings arranged themselves in a circular pattern. I hope you remember this. So this was Oyster experiment, guys. All these experiments were called as the Oyster. These were conducted by Oyster, so Charles Henry Oyster. So this guy, Henry Oyster. So this guy gave this theory. Yes, when a current carrying conductor. This was your previous chapter, the magnetic effects of electric current. So he stated that when a current carrying conductor is current carrying conductor is present, there exists a magnetic field B perpendicular to the direction of current, right? So whenever there is current through a conductor, when there is a current carrying conductor, there exists a magnetic field B which is perpendicular to the direction of the conductor. Hope guys you know this. So this was the theory which was given by Oyster. So what happened? So there was a conductor, and whenever the current flows through this conductor, there exists some magnetic field B which is perpendicular to that of conductor. Hope guys everyone knows this. Yes. Click on S. Come on, click on S. Right? Yeah. Now, okay, there was another guy. So yes, there was okay. Oyster published this. Okay, Oyster published that whenever there is current carrying conductor, there is magnetic field. Okay, fine, sir. Now, why can't the converse be true? Can the converse be true? Yes. Can the converse be true? What is converse, guys? Say I have a current carrying conductor. In the presence of some current, yes, there is magnetic field. Yes, exactly, Hariprasad. So the converse is, if I have magnetic field, will there be current in the conductor? Say I have a current carrying conductor. Now there exists a magnetic field. Now, if I keep a magnetic field, will I get the current in the conductor? So is this now? Before that, tell me, is this magnetic field? Is this magnetic field stationary or moving? Is this magnetic field stationary magnetic field or moving magnetic field? I mean to say, is this magnetic field continuously circling or is it stationary? So if it's moving, why should we require a motor? Okay, guys, yeah, see, if it was moving, it should also move the iron filings also in that direction, right? So here the magnetic field is stationary. Okay, it's stationary. So there was this guy Faraday, who thought that, okay, sir, now, yes, Oyster said, you said there is, whenever there is flow of current, there exists a magnetic field. So maybe that is stationary, maybe that is stationary. Now, if I keep a magnetic field, will there be current? So this was the question asked to Oyster. Then Oyster thought, oh my God, I don't know the answer. So then Faraday said, okay, I'll try to find it. Come on, I'll try to do this experiment and I'll find the answer. So Faraday went to his lab and he did few experiments. So in first part of this chapter, we'll be learning about Faraday's experiment. So in first part of this chapter, we'll be learning Faraday's experiments. So Faraday conducted 3 experiments. Okay, we'll be learning all 3 of them. Then we'll be deriving the mathematical expression of the current formed. So whenever there is current, guys, there should also exist voltage, right? Whenever there is current, there should also exist voltage. And we have discussed in the previous class that the voltage, so conversion of one form to the other form. Say, whenever we convert one form of energy to electrical energy, what do we call it? We call it as EMF. Okay, whenever we convert an energy from one form to the electric form, we call that electric form of energy as EMF, electromotive force. Okay. So yeah, so whenever there exists current, there is requirement of EMF. This EMF, whatever the EMF we get, what is the expression for that EMF? How do we quantify that EMF? So that formula would be learned in today's class. I mean, in this chapter. Then there is something called as back EMF, that is learned by Lenz's law. There exists a negative sign, so we'll learn about that, and we'll also learn about applications of EMI. So that all these would be learned with Faraday's experiment and Faraday's laws of EMI in this first part. In second part, we'll be learning about what are the applications of this electromagnetic induction, say like the transformer or the motor or any other applications we're using in today's life. All are applications of Faraday's law. So how is it? So we'll learn that. Then finally, we'll learn about something called as solenoids, inductors. Then we'll learn about connection of series and parallel of inductors, and also LR circuits, inductor resistance circuit. Likewise, we studied in our previous class the RC circuits, right? Resistance capacitance circuit. Similarly, we'll be learning about inductors, resistors circuit. Okay. Okay. So let's quickly start this session with the recall test, guys. Come on. So I gave a brief introduction of what we are going to learn and why it is important. So please give answers to these questions. Okay. Come on, guys. I have launched the poll to you. So if a charged particle at rest experiences no force, if a charged particle is at rest and it experiences no force, which one of the following 4 options suits the best? Always. So this is how, by choosing that particular answer, you guys fall to the trap. Yes. So whoever chose option A, all of you have fell to the trap. Okay. Sir, how did we fall to the trap? Okay, come on, guys. Cool. So very good, guys. Very good. So yeah, going to end the poll. Yeah. So most of you have answered option A, and one of you have answered option C, and option C is the correct answer. Okay. Why, sir? Why is option C correct answer? Sir, Acha, please tell me what is the force experienced by a charge when it's in the presence of magnetic field? So just now we learned that, right? So in the presence of uniform magnetic field, what is the force experienced by a charge? It's going by F is equal to Q into V cross B. Okay. F is equal to Q into V cross B, where velocity and magnetic field both are vector quantities. Okay, correct. Krish Modi, correct. Ramakrishna Reddy, and I don't know why Madhavi and Bhargav removed their answer. Cool, chalo. Yes. So F is equal to Q into V cross B. Okay, Rakesh, I hope could change. Yeah. So yeah, what's happening here? So if a charged particle is at rest, when the charged particle is at rest, what is its velocity? Its velocity is 0, right? Yeah, its velocity is 0. Okay, Its velocity is 0. Now, if its velocity is 0, what happens to force? Force will obviously be 0. Now, they are not asking about the force, they are not asking about the charge, but they are asking about the magnetic field. Achha, what's happening to the magnetic field? So, the magnetic field here may be uniform, may not be present, or may be present. So, we don't know that. But the charge is at rest. So, at these cases, guys, whenever you find questions like this, everyone tend to make the answer or give the answer as the magnetic field is 0. But no, we don't know about the magnetic field. See, when my velocity is 0, my force was 0. Yes, when velocity is 0, force is 0. But they did not mention anything about the magnetic field, okay? They did not give any information about magnetic field. So, you can't come to a judgment that magnetic field is 0. So, here, you should give an answer which is confusing. Yes, it is the trick. So the magnetic field may or may not be 0. So this is very easy question. This is a very easy question. But if you mark option A, you will get -1 mark in your JEE mains. Right? Anyway, you are losing mark. See, in JEE mains is such an exam where you may get, if your answer is correct, you may get +4 marks. But if your answer is wrong, you may lose -1 mark. I mean, you may lose 1 mark. So this way, please don't go to quick decisions. Wait, check for all the options, then give the correct answer. Okay. So here option C is the right answer, guys. Cool. Yes, hope everyone have understood this. Okay, let's go to the next question. A charged particle is moving along a magnetic field line. The magnetic force of the particle is. Now this is again a good question. I hope everyone would not fall to the trick. But let me see. Okay, guys, please try to answer this question. So whenever you answer the question, I'll get the confidence that yes, our students are learning and have given I mean, they have participated and they are. I'll feel confident enough that students are perfect and they can answer now. At least please try to answer it. If your answer is wrong, never mind. Never mind for your wrong answer. Okay. Please always give the answer. Okay. Okay, guys, come on. Please think. So those who gave the answer, also please give them the chat box so that I can verify your answer. Those who answered, also please give in the chat box so that I can verify your answer. Yes, correct, Krishmori. Very good. Krishmori, very good. Others? Okay, guys. Yeah, it's almost 1 minute up. Yeah, I'm going to end the poll, and yes, here is the result. So most of you have selected option A and option C and some option B too, but correct answer is option B, right? So what's happening? A charged particle is moving along a magnetic field line. The magnetic force of the particle is. So guys, we are doing what? So again, give the same expression. F is equals to. So this is the magnetic field and charged particle. The charged particle is in the presence of magnetic field. Okay. Now, in which direction is the magnetic field? I mean, this charged particle moving. Say, have a charged particle and have a magnetic field. Now, in which direction is my charged particle moving? Yes, very good, Rakesh. See, my charged particle is also moving along the direction of magnetic field, right? My charged particle is also moving with some velocity v along the direction of magnetic field. So what is the angle? What is theta? What is theta, guys? Come on, answer. Please reply. What is theta? The angle between magnetic field and the velocity. Yes? Exactly, Krish. Superb. So what is my theta, guys? 0. Yes, theta is 0 degree. So we know that force F is equals to Q into V cross B. Q into V cross B. So what is Q into V cross B? It's F is equals to Q B B sine theta. Now theta is 0 degree. Yes, F is equals to Q B B into 0. Oh my god. This is sine theta. Sine 0 is 0. So though my charge is not non-zero, though my velocity is non-zero, though my magnetic field is also not zero, but angle here, the angle is 0 degrees. So my force will be Papa Chi force is 0 newtons. So the answer is option D, guys. Cool. So please, again, please check your answers. Please note that check for all the options. Okay, check for all the conditions and check for all the options. Cool. Yes. Okay. Let's check the next question. Okay. So okay, I think yeah, a moving charge will produce. So again, an easy question. Come on, guys. An easy question. Come on, try to answer. Cool, very good. Sir. Yes, I have launched the poll again for you guys. Come on, try to answer. So, moving charge will produce dash. What is being produced by moving charge? Yes, Hariprasad, super. Madhavi, super. Very good. Rishmodi, super. Very good. Here also, yes, guys, super, super. All okay, all correct. Okay, cool. Okay, then most of you have given the right answer. Yes, option C, both of them. So there exists some electric field because of the charge alone, and when the charge is moving, it generates magnetic field. Okay, that's it. Next, fourth question, guys. Come on. So fourth question goes like this. So I have launched four for you guys. So fourth question is: a flow of positive charge in one direction is equivalent to the flow of an equal fill in the blanks. The flow of positive charge in one direction is equivalent to the flow of an equal dash. Say have a conductor, have connected a battery, so there is all positive charges which is flowing in this direction. So my current is in this direction. So when my current flows in this direction, what is being flown? What's happening? Krishmurti check. Okay, Krishmurti correct. Ramakrishna, did you check your answer? Okay, okay, that was answer for previous question, right? Okay, cool. Here, guys, come on, come on. I hope everyone have given the answer. Please try to give the answer. So I have drawn a drawing for you guys also. Please check that I have drawn a drawing. From this drawing, you may recollect something. So the flow of positive charge in one direction is equivalent to the flow of an equal right. Yes, correct, Hariprasad. Guys, come on, here. Zoom audience also, you could give confirmation answers in your chat box if required. Otherwise, you could give in the polls alone. Waiting for polls, guys. Madhavi, check. Okay. So let's discuss. Okay, I'm going to end the poll and sharing results to you guys. So most of you have given option A, but option A, why? Which why option A? Okay, there you go. So here I have all positive charges, right? So here I have all positive charges which are moving in this direction. Now, an equal amount of, say if I have negative charges, can these negative charges also move in the same direction? See, whenever there is positive charges, so these negative charges, where are they attracted to? Where are they attracted to? Check that. Or where are they repelling from? Check that. That's enough. See, if my negative charges also go in this direction, will they be allowed into the battery? It will repel, right? Guys, see, the negative charges will be repelled from the negative side of the battery, right? See, it will be always attracted towards the positive side of the battery. So, option will be same amount of negative charges, equal negative charges in the opposite direction of positive charges. Okay. So, option B will be the correct answer for this. Yes, okay. Yes. Hariprasad, what? Okay. Okay, guys. So this, I hope everyone have understood. Just next first question, guys. A source which gives a constant potential difference and hence flow of charges. So I have a force. I have a source which gives constant potential difference and flow of charges. So there is constant potential and uniform flow of charges. What is it? What it is? Okay. So I hope you guys require phone for this. Yep. Okay. I've lost the phone. Yes. Cool. 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 Very good. Very good, guys. Come on. Awesome. Awesome. So yep. The answer is option A. Yes. The source of EMF. Okay. Cool, guys. So next we'll go to, yes, this is your option C, D, C, B, A. You could verify again. So yeah, next we have to start with the basics. So magnetic field lines and magnetic flux. So guys, similar to that of electric field lines. So we learned about electric field lines. So whenever there exists a charge, there exists electric field lines in all directions. Say if I have a charge Q, there exists electric field lines in all directions, and it's denoted by capital E. Now, if this charge tries to move with some velocity v, there exists. So what happens? So what happens when this charge tries to move? So there will be presence of some electric field, and perpendicular to this electric field, exactly perpendicular to this electric field, there exists some magnetic field. Then yes, so there exists a magnetic field in this direction. Okay. So exactly perpendicular to this, there will be existence of magnetic fields. Okay. Now quickly tell me, what is an electric flux? What is phi E? I think we have discussed about this in detail in our previous chapter of electrostatics. We had discussed. So what is phi E? What is phi E? Or flux, electric flux. I'm asking about electric flux. Electric flux ಏನು? So what is electric flux, guys? Come on, tell me. Phi E. What is electric flux phi E? Okay. So there is some problem with sign graph. Cool. Let's draw. Yeah. Whenever there exists a DC current, okay, we have not yet discussed about the AC current. So let's keep it DC. So whenever there exists electric field in this direction, perpendicular to this, there exists a magnetic field. Okay. Good. So we can show that with number of lines. Okay. Okay, cool. Let's anyway remove that. So yes, correct. Tejas, Rakesh, who else gave me the answer? Rakesh, Tejas, Anu. Yes, very correct. Very good, guys. Super. So this is my electric flux. Yes, electric flux means nothing but phi E is equals to the total number of electric fields. Say if my uniform electric field exists. Yes, number of electric field lines passing through the given area, that is E dot A. Phi E is equals to E dot A. That is, what is phi E? Phi E is nothing but EA cos theta. So guys, I hope everyone remembers about area vector. Say if I have an area of cross section A, then there exists this area can be written as a vector with magnitude as area of the area of this surface, and direction is which direction, guys? Come on, tell me. Direction is, and the direction of this area vector, say if I have an area like this, the direction of this area vector is, yeah, correct. So always normal to the surface area. Yeah, normal or perpendicular to the surface area. So if this is my surface area, then normal to this surface area or perpendicular to this surface area will be the direction of your area vector. So these are the few things. So flux is nothing but E dot A, electric flux. So we discussed all these for electric flux. Now we'll discuss about magnetic field lines and magnetic flux. So yes, guys. So there was magnetic field line. Say if there exists some moving charges, or if I have a bar magnet. So if I have a bar magnet, so what happens? There exists something called as North Pole, and there exists something called as South Pole. Yes, correct, Hariprasad. Very good. Ramakrishna Reddy, correct. Very good. So yeah. So how do we get a magnetic field line? So for magnetic field line, we have several ways. One such way is a bar magnet, so which was supposed to be taught in your previous chapter, but that might have been taught in your CBSE class. So there exists a bar magnet. So guys, tell me something about bar magnet. So in the bar magnet, similar to that of an EMF, when the electrons or positive charges are emitted from positive plate and are being attracted to the negative plate, I mean the electrons are being, positive charges are being collected back at the negative plate. Similarly, in magnet also, the electric field line starts from north pole and ends at south pole outside the magnet. So guys, I'm mentioning the electric field line starts from north pole and ends at south pole outside the magnet. Okay, so this electric field, this magnetic field has a double life. Okay, so the electric field starts from the north pole and ends at south pole outside the magnet. Then what would happen inside the magnet, guys? What will happen inside the magnet then? Outside the magnet, it's from north pole to south pole. Similarly, from inside the magnet, yes, it is south pole to north pole. Okay, inside the magnet, there exist magnetic field lines which are moving from south pole to north pole inside the magnet. But outside the magnet, it's north to south. So this is one of the way to get the magnetic field lines. Now, if I bring this magnet, say if I bring this magnet near a surface area, say I have a plane surface, near this surface, if I bring this magnet, what happens? Yes, correct, Madhavi. Cool. So if I bring this magnet near the surface area A, so there are three magnetic field lines passing through this area. So if this area is 1 units, if this area is say 1 meter square, okay, have a 1 meter square area. In this 1 meter square area, how many electric field lines are passing? Please check that. There are 1, 2, 3 electric field lines are passing through this surface area. Then what can we say about the flux, guys? So there exists something called as magnetic flux. Okay, there exists something called as magnetic flux. So this magnetic flux is similar to that of the electric flux. So it is the number of magnetic field lines passing through the given area of, passing through the given surface area is called as magnetic flux. So magnetic flux is denoted by phi b. Okay, it's denoted by phi b. So electric flux was denoted by phi e. Magnetic flux will be denoted by phi b. That is equals to the strength of the magnetic field. So here the strength of the magnetic field is given by B. Okay, so B, this is also called as magnetic field density. Okay, it's not only magnetic field, it's fully called as magnetic field density. Okay, so this you might have studied in your CBSE. B is called as magnetic field density, and there is also something called as H. What is H, guys? So B is called as the magnetic field density. There is something called as H. What is H here? Yes, H is magnetic field intensity. Okay. Sir, okay, you may ask, sir, what is the difference between density and intensity? Yeah, exactly. So yeah, so H is called as magnetic field intensity. Okay, so these are the terms which you have studied already in the previous chapters. So here B is magnetic field density. So the flux 5 is given as V dot A, that is VA cos theta. So if I have, so how do we calculate that? So that's being represented here. Say if I have a surface area, then in this surface area, if I have to calculate the flux, what I'll do, I'll first consider a small area A. So consider a small area M. in this total surface area, I'll consider a small surface area dA, and I'll calculate what is the, okay, here this dA is represented by the word ds. Okay, so the instead of a the surface area is represented by s here. Okay, that's the only difference. Instead of a, the surface area is represented by s. To say it's the short form for SA, surface area. Surface area na S anta denoted. So they have denoted surface area as S. So if we consider a small, okay, let me also consider that as S. If S is the surface area, then small surface area is called as ds, and the magnetic field. So guys, we had learned in detail about the electric field and electric flux. Same rules apply here. Same rules apply here. Even the same Gauss's law also exists for magnetic field. The same Gauss's law which we learned for electric field is the same thing which we are going to apply for magnetic field also. Same to same theory. Only change is, instead of electric field E, there is magnetic field B. That is the only change. Otherwise, everything will be same. Okay. Hope everyone remembers. So yeah, my magnetic field B is perpendicular to this, and small, it's moving in a small direction. So if I integrate this area, what I'll get? I'll get the entire area. So my flux can be written as phi b is equals to integral v dot ds. So since so this phi b is written as phi b is integral v dot ds. So we know that v dot ds is v ds cos theta, right? So here again my magnetic flux is constant. So what happens further is flux phi b will be equals to b times of integral ds and sorry, b cos theta into integral ds. Okay, here b cos theta into integral ds. So if you check that, what will you get? Phi b will be equals to what? Phi b will be equals to b dot a. Integral of ds is nothing but total surface area s. So still I'll call my surface area as a only because I'm familiar with that. So phi b is equals to b dot a, or if I want to say according to them, then it is b dot s, where s stands for area. S and a are same. Okay, cool guys. So if I want to find the small surface area, say in this small surface area, if you want to find the small magnetic field dp or d phi b or small flux d phi b, then the small flux d phi b is b dot ds, that is b ds cos theta. Okay, this is the things. So everything which applicable for electric field is the same thing which is applicable for magnetic field, and electric flux and magnetic flux also. Okay, so guys, what do you remember from this diagram? I hope we had seen this diagram, right? Previously we had seen this diagram. I hope everyone remembers this. So this shows the factors on which the magnetic flux depends on. Hope everyone remembers that. Yes, guys, do you remember? Okay, let me note down. Factors of phi b. What are those? The magnetic flux depends on one. Tell me. Okay, similar to electric flux, the magnetic flux depends on what? Yes, the surface charge density itself, or the strength of magnetic field B. Okay, this is first one. Second one, guys, come on. If more the strength, so if strength is more, then flux will also be more. That is what it says. If B is more, phi B will also become more, right? Next up, come on, guys. I want answers. Come on, come on. Please give. Yes. Next is area. Correct. Correct. So if area, if S increases, so if S increases, flux phi B also increases, right? If S increases, flux phi B also increases. Third thing, what was the third thing? What is the third thing in which my magnetic flux depends on? Yes, the angle, right? Very good, guys. Very, very good. So the angle. So the angle, if theta increases, what happens to cos theta? Okay, if theta increases, cos theta decreases, or if theta decreases, cos theta increases. Okay, So it depends. So my flux also depends on angle. So it depends on, I can say cos theta. You can say cos theta. If cos theta increases, phi b increases. Okay, cool. So for cos theta to increase, theta should be decreasing. So these are the three factors which my magnetic flux depends on, and hope everyone remembers this from electric flux concepts. Yes. So that's what is being explained here. A planar area vector S normal making an angle of theta with magnetic field of strength B, and magnetic flux is then given by phi is equal to B dot S or Bs cos theta. Okay. Okay, cool. So I have a concept test for everyone. Please try to answer. Say a flat metallic plate has an area of 10 meters square is placed in an XY plane. The magnetic field is given by B is equal to 12 Tesla in the positive Z direction. Find the magnitude of flux passing through the plate. So let me give the situation. So what's happening? Now let me consider X, Y, and Z planes. Okay, X, Y, Z. Okay. So there it is, the XYZ plane. So a flat metallic plate. So let me draw a flat metallic plate here. Okay, this flat metallic plate is here. So this is a flat metal plate. Now there exists so a magnetic field of how much? So let me draw that magnetic field. So there exists some magnetic field B of 12 Tesla. Okay, the magnetic field is B is equal to 12 Tesla. Now, how much is the flux? What is phi b? What is phi b? Phi b is what? Vishmuli correct? Hariprasad correct? Guys, come on, try to answer. Zoom audience, please come on, try to answer. Come on, guys, come on, you can do it. Okay, cool, Rakesh, very good. Okay, Ramakrishna Reddy, superb, awesome. Did we discuss about that? Okay, we did not discuss. Okay, super guys, very good. So the answer is phi b. So phi b equals to 12 Tesla into area is 10 meters square. That is 120 units. So we didn't check the units. So this SI unit for flux. Okay, not ordinary flux. For magnetic flux. Yes. What? Weber. Okay, we'll learn about Webers in detail in the upcoming part. So yes, area of cross section. So here they have considered XY plane in the bottom part and Z plane in the upper part. So this is the surface area and area vector is in this direction. So my theta will be equals to 0 degree. Yeah. Again, BA cos theta, right? So this is cos 0 degree. Why is it 0? My area vector and the magnitude of magnetic field. So the magnetic field and the area vector is both in the same direction. So my theta is 0. So my magnetic flux will be 120 Webers. So the SI unit of flux is Webers. Okay, Weber. Flux. Phi b is Weber. Okay. So guys, so there are few quick notes on magnetic flux. So magnetic flux is a scalar quantity. So magnetic flux is a scalar quantity. Dot product of two quantities is always a scalar quantity. Okay, phi is b dot a. So dot product of any two quantities is always a scalar. We have already learned that. So the SI unit of magnetic flux is Webers or Tesla meter square. So we know that phi b is nothing but b dot a. If you see the SI unit of magnetic field is Tesla and the area is meter square. So the flux is nothing but the SI unit of flux is Tesla meter square. Okay, thus we get for magnetic field in your previous class maybe. The other unit of magnetic flux is Webers, WEBER, Weber. So in your previous section or previous classes of we didn't take, but it's in your CBSE you might have learned the magnetic field is given by Weber per meter. Okay, See, so the other expression for magnetic field, so we know that phi b is equals to b dot a, right? So if we solve for b, b will be equals to phi b divided by a, that is Webers. So if we try to write the SI units, not a, so we have Webers per meter square. Okay, actually it should be Webers per meter square, right? Yes, I think it should be Webers per meter square. So unit of magnetic field is Webers per meter square. Okay, cool. So yeah, see in the special case, yeah, in a special case in which B is uniform and over a plane surface with total area S, then if B is perpendicular to the surface area, so if the magnetic field is perpendicular to the surface area, then the area vector will also be perpendicular to it, to the surface area. So the angle between the magnetic field and the surface area will be 0. Theta will be obviously 0 in that case. So cos theta will be 1. So in that special case, we'll be having flux, magnetic flux phi b is B into A or B into S. B dot S. B S. B S. This is much of your flux. Cool. So let's come to Faraday's experiment now. So yeah, as we discussed earlier. So what happened? So Faraday was thinking about the converse of Oyster's experiment. Okay, Oyster's experiment. So what happened? So there's a story, guys. I hope most of you might have learned this story or have heard this story. So one day, actually, what happened? This guy Faraday was doing experiments. So what he did, he took a coil. Okay, what he did, he took a coil and he connected a galvanometer to this coil. Okay, connected a galvanometer to this coil. He did not connect directly. He connected with a plug key. Okay. Now, first what he did, he connected the gal. Okay, always what he did, he took a magnet. Okay, in this experiment, in Faraday's experiment, this is what we had heard. So he took a bar magnet. So there is a bar magnet. Now, this guy Faraday, yeah, he took his bar magnet with North Pole and South Pole. Now he tried to insert this magnet into this electric field. So earlier in Oyster's experiment, he said, yeah, we said that whenever there is current in conductor, there exists a stationary magnetic field. So there exists a stationary magnetic field. So what was Faraday's idea? Faraday's idea, Faraday thought. So if there is some magnetic field, so if I keep a stationary magnetic field, say if I keep a stationary magnetic field in the coil, it may give me some current. So what he did, he took the coil and he kept the magnet inside this coil. So he took the coil, he kept the magnet inside this coil with north and south pole. Then what he did, he took his galvanometer and after keeping the magnet, he connected the key. Okay, so I hope most of you might have not heard this. So this is what he was doing. So after keeping the magnet, he used to connect the key to check. There is deflection, there is deflection. So for how long will he wait? So this was. I don't know whether this story is true or false, but I have heard this. This is what had happened. So what happened? There was this coil. He kept the magnet first, then he connected the key. Will there be any deflection in the galvanometer? Will there be any deflection in the galvanometer? Obviously no. Right? There won't be any deflection. So he tried this experiment for so long. Oh my God. He did this experiment, repeated. Every time he tried to connect the key only after connecting the galvanometer. I mean, only after placing the magnet inside the coil. So he didn't get. So one day what he did, okay, he had this empty thing. So he had plugged the key and he was fed up of his experiment. So what he did, he threw this magnet. He threw the magnet into a cup. So there was some cup here. So he tried to throw this magnet from here to this cup. Voila. Yeah. So he tried to throw this magnet. Then he found something new. What happened there? He found that he had not removed the key. The key was still there. So he threw the magnet. He saw, oh my God, there is some deflection in the galvanometer. So there was some deflection in the galvanometer. Oh my God, all this time I was doing something wrong. Now he checked that, okay, now I got to know. So he conducted his first experiment and he published that when a bar magnet is held, okay, he gave this conclusion. So when a bar magnet is held stationary near a coil, no current will be flowing in that coil. Okay. If he take the bar magnet and kept held stationary inside the coil. So what he did, he took this magnet, he conducted this experiment. So he connected, so here they have shown a bulb here, but in actual, he had connected a galvanometer because this much amount of current is not enough to light up a bulb, okay? Guys, this much amount of current, whatever, when we put the bar magnet, it is not enough for a bulb to glow. So it requires very, very, very huge energy. So that was not possible to get from this side. Okay, so he connected a galvanometer. Okay, actually he connected a galvanometer. So he observed that whenever he tried to move that magnet, so he got a new thing to play with. So he took the magnet, inserted the magnet inside the coil, removed the magnet. So he saw that, okay, when he inserted the magnet, there was deflection in the coil only once. What happened? There was deflection in the coil, but it happened only once. Then he kept the magnet inside the coil, okay, stationary coil. He kept the magnet stationary inside the coil. Now he observed that, there is no deflection. So so he gave this conclusion: when a bar magnet is held stationary near a coil, there will be no current flowing in the coil. So as the magnet moves, so this was the first statement which he gave. The second statement which he gave was, as the magnet moves with respect to the coil, there will be some flow of current. Okay, so he observed this. Okay, he observed this when the magnet was moved. When the magnet was moved, there was some current inside the coil. So then he gave this theory, the Faraday's law. How many of you remember Faraday's law in your 10th standard? The Faraday's law. Hope many of you might have done the by heart of this statement. So the rate of change of magnetic flux linked with the coil changes, and EMF will be produced in the coil. How many of you, honestly tell me, how many of you had by heart this statement for 5 marks, including me? Yes, even I did. Okay, so yeah, right? The Faraday's law, yes. So now guys, now we'll use the same law. So what does it means? The rate of change of magnetic flux or magnetic field linked with coil changes, comma, and EMF is produced in the coil. Right, now we will study that in detail. So what happens? So we are observing here, when the stationary magnet is brought near, okay, when the magnet is made move, or when the magnet is, okay, not by heart, okay, cool. Okay, so the rate of change of magnetic field. So what does rate of change means, guys? Rate of change means the continuously changing magnetic field. Okay, rate of change here means the continuously changing magnetic field which is linked with the coil. So this magnetic field should be linked with the coil. Only then there will be change in EMF. And this change, okay, when the coil changes, there will be production of EMF. Only when the coil linked with the, only when the magnetic field linked with the coil is changing continuously, it will produce some electrical energy or EMF. Okay, this is what Faraday's first law meant. So the direction of current. So the direction of current changes depending upon the motion of the pole. So when I bring a north pole near this coil, the current direction will be in one direction. When I bring south pole near this coil, the current direction will be opposite. Okay, so we learn about that in our next classes. So what happens? So let me give a brief idea. So say consider this coil and this north pole. So guys, how do we write N? N is written like this, right? In your textbook, you might have seen this. So if you try to curve the N, so if you try to curve this N, you will get two ends. Put arrows to those two ends. Okay, you could see that whenever I insert a north pole to the coil, the current or the movement of charges is in which direction? Yes, it is anti-clockwise. So the current will be anti-clockwise. Suppose, so when N is approaching, when the north pole is approaching, it will be anti-clockwise. When N is leaving, what happens? If N is leaving, entering, leaving. So entering will be anti-clockwise, then leaving will be, if entering is anti-clockwise, if north pole is leaving, see, observe this, north pole is entering, all the charges are moving anti-clockwise, but when the north pole is leaving, all the charges are moving clockwise. Okay, so entering will be anti-clockwise, leaving will be clockwise for north pole alone. Okay, so I'm talking about only north pole. Okay, guys, exactly opposite would happen with south pole. So if I am inserting south pole entering coil, then draw the south pole in a curvish way. So you could see that S means south. So it is clockwise. While entering, it will be, the current direction will be clockwise. While leaving, while north south pole is leaving, it will be anti-clockwise. Okay. So what happens if you place charged non-metallic body in place of magnet? Yeah, that is what Faraday's next experiment is. So what happened? Okay, Faraday gave the statement of his first experiment, that is relative motion between the coil and the magnet induces a current in the coil. So the relative motion between the coil and magnet will induce an EMF in the coil. So this is Faraday's first experiment. So we'll go to the second experiment. So I hope everyone knows what an electromagnet is. Yes, I hope everyone knows what is an electromagnet. What is an electromagnet? Again, we studied this in your 10th standard. So guys, how many of you tried? I had tried this. So how many of you tried the electromagnet? So let me show here this slide only. I hope most of you might have tried an electromagnet. So this was a syllabus in your 10th, right? So what is an electromagnet, guys? What is an electromagnet? Electromagnet and the it's a temporary magnet, okay? It's a strong magnet, okay? So how can I make one? So can you help me make one? Tried but failed. How many of you tried and failed? How many of you tried and failed? Okay, there might be many engineers, many scientists, I can't say engineers, many scientists who have tried this electromagnet. So hearty congratulations to you guys. You have tried something new in your 10th standard only. So you are made for research. Please do that. Okay. So how to do a magnet? How to do a magnet? Yes. Take an iron piece, small iron piece. Okay. Take an iron piece and take take a coil. Take a wire and coil over this iron piece and connect this one end of iron piece to a battery. Another end, okay, connect both ends of iron piece, wire to the battery. So there will be positive and negative with voltage V. So there will be current flowing inside this, and this will generate, this will make a magnetic field. This will create a magnetic field with positive part wherever you connect the positive. Wherever you connect this positive lead of battery, or wherever you connect the positive terminal of the battery, that positive terminal will become north pole and the other end will become south pole. Okay, this should be north, this should be south. So this was a construction of electromagnet. Okay, so yeah, even if you remove the iron piece, even then this experiment, whatever you learned as an electromagnet, will exist. Okay, so Faraday used the same thing. Instead of using a bar magnet, he used an coil, ordinary coil. He took a coil and connected to a battery. Now this coil become an electromagnet. Okay, this is an electromagnet, and he repeated the experiment with the same electromagnet. He tried to change the magnetic flux into the coil. Then an EMF was produced. So just like the case of an ordinary magnet or a bar magnet, there was current induced only when there was relative motion. So only when the coil was moving, there was relative motion between the closed loop of the coil, which is connected to the bulb, and the electromagnet. Only then there was some EMF produced because of the relative motion. Okay. So relative motion between a current carrying loop or current carrying coil, and so this is called as the current carrying coil or the electromagnet, and a closed loop induces current in the coil. This is the conclusion which was given by Faraday, and this is Faraday's second experiment. Okay, so next we will be having Faraday's third experiment. So instead of moving the coil, what he did, instead of moving the coil, Faraday did not use such things. So what Faraday did was, he took the primary coil. So guys, yeah, he took one coil and he took this second coil. He connected the second coil with a galvanometer. Okay, he connected the first coil. Okay, he connected the first coil with a battery and a switch. Okay, so he didn't make such an arrangement. He connected a battery and a switch. Okay, voltage and a switch. So what happened? Whenever he turned on the switch, there was current flowing in this. There was some magnetic field set up. So this magnetic field which was set up, okay. So there was current flowing in this, and there was magnetic field set up. This magnetic field which was set up linked with the secondary coil. So whenever he tried to turn on and turn off, whenever he turned on, there was magnetic field generated in this way. So whenever he turned off, there was no magnetic field. Okay, this way, there is change in magnetic flux. Okay, so what did Faraday say? The rate of change of magnetic field, right? So the rate of change of magnetic field. So please note this statement. This statement is very important. He said change of magnetic field is required. Time varying rate means, so wherever you find the word rate, it means just time varying. Okay, it varies with time. Time जो है change आता होता है. It varies with time. Rate just simply means time varying. Also, in your physics in 11th standard, rate of change of displacement is dash. What is it, guys? Rate of change of displacement, you know. It was velocity, right? Right? So when we change our speed, or when we change our displacement, when we are trying to move, with respect to time, there was existence of velocity. So how did we write velocity? We wrote velocity as v is equals to dx by dt. Remember, v is equals to dx by dt, right? Here, what I wanted to say is rate, which is time varying, also means in maths it's nothing but differentiation. Okay, in maths it's nothing but differentiation. So what is meant here? If I have a magnetic field, if this magnetic field is varying with time, then there will be production of EMF. So current is induced in a closed loop when the current starts flowing in the coil. So current is induced in a closed loop when current stops flowing in the coil. So these are the two conditions. So when I turn on, there is flow of current in one direction. When I turn off, there is flow of current in opposite direction. This way, yes, even in this case and even in this case, in both cases, when current flows in one direction and flows in opposite direction, in both cases, there is change in magnetic flux or magnetic field. This change in magnetic field will induce current. So this simply says the time varying magnetic current. So the time varying current in the coil induces current in the closed loop. So the time varying current. So the time varying current will give time varying magnetic field, right? Guys, tell me. I hope most of you by now have learned solenoid in your CBSE class at least. You might have learned about solenoids. Yes. Again, we'll learn about the few problems in solenoids. A solenoid is nothing but a loop of wire. A solenoid is nothing but a loop of wire. It produces magnetic field as B is equal to mu naught Ni, or B is equal to mu naught Ni upon L. Hope everyone knows this. So where N is number of turns per unit length, that is N by L. Say if my current is varying, if my current is varying, my magnetic field will also vary according to this formula. Okay. So the time varying current in the coil induces current in the closed loop. So this time varying current will induce time varying magnetic field. Then this time varying magnetic field will induce current. Okay. Okay. Cool. This is Faraday's third experiment. Guys, if you see this setup, where have you seen such thing? Have you seen this thing somewhere? Have you seen the same thing somewhere? The same setup somewhere? I bet everyone have seen this. Please think of that place. Where do you think have you seen this? Same working principle, same thing, same exact thing. So that's an electrical device which we use in our day-to-day life every day. Without that, we can't survive. Which is that device? It's the 95% efficient device. That's the only device which is 95% plus efficient. Okay. So which is that device? Which works exactly like Faraday's third experiment. So these were the three experiments conducted by Faraday, guys. And we are using all three experiments in different way for different applications. We'll be learning about their applications, and we'll be learning about the mathematical formula of Faraday's law. So I'm waiting for answer yet. Have you seen this setup anywhere? Have you seen this setup? Even today we are using. Yes, exactly, Hari Prasad. Exactly. So this is similar to that of a transformer, right? So in one end you have the primary coil, in second you have the secondary coil. So the time varying magnetic field in the primary coil will induce the time varying current. I mean, the current applied in the primary coil will induce some voltage in the secondary coil, and it is being transferred, right? So yes, transformer is the application of this experiment. Okay. So conclusion: current is induced in a conducting loops. Okay, current is induced in a conducting loop because of changing magnetic flux inside the loop. Again, guys, please note this experiment. There is something peculiar. Say whenever there is this guy, whenever he tries to enter the coil, only then there will be production of EMF. But when he is moving in upward and downward motion, so if we try to move in upward and downward motion, there is no EMF. But when he tries to move inwards and outwards, EMF is generated. Right? So, yes, whenever we have, is my screen not visible, guys? So, whenever we have the flux, the magnetic flux should cut the coil, okay? So, whatever the magnetic flux we have, see, all these dot dipoles are nothing but flux, okay? So, whenever this flux cuts the coil, only then there will be EMF generated. If no flux cuts the coil, then there won't be EMF generated. Okay. So this is what Faraday's experiment says. So there is from Faraday's experiment, there's a question. Guys, try to answer this question. Okay. Out of these three rings, A, B, and C. So we have three rings, A, B, and C. Out of these three rings, which of the ring will have the least or minimum magnetic flux? Which of these three rings, A, B, and C? Say I have a bigger ring in which I'll read out the question for you. A large loop of wire in figure carries into and out of a lamp. So carries current. Okay, here it should be current. Carries current into and out of the lamp. So there is some current flowing into and out of the lamp. Okay. There is this current flowing into and out of the lamp in a closed loop. Okay. So whose direction alternates? Now, guys, yes, they have mentioned one more condition. The direction of current alternates. Okay, back and forth. So if the direction of current alternates, there exists alternate magnetic field also, right? If current is alternating, magnetic field should also alternate. Then, if there is presence of alternating magnetic field, then what should exist? There should exist some EMF. So, which one of A, B, and C will have less EMF or less magnetic flux? Guys, okay, Prakash, want to check again? Please use the formula, okay? Please use the formula of flux. Phi is equals to B dot A. Please use the formula of flux, or phi is equals to BA cos theta. Please use this formula to verify. No. Prakash Gowda, no. Rakesh, no. Please check your answers. So they are asking the minimum, okay, which is the minimum one. Say the area of each ring is same. All rings are same. A, B, C, all rings are same. Correct, Madhavi? Madhavi, correct? Ramakrishna Reddy, correct? Yes, guys, correct. So most of you have given the right answer. So the answer is C. Okay, the answer is C. Why C? So we know that flux phi is equals to B dot A, right? Or phi is equals to BA cos theta. Now, guys, if you see, there is current flowing. Yeah, we know that there is current flowing I in this direction. Now I have the ring C here, the ring C, with area of cross section A. What is its direction of? So guys, what is the direction of my area vector here? Here we have to consider theta, right? So I know the magnetic field will be in this direction. So if current is in this direction, where is my magnetic field, guys? If current is in this direction, where will be my magnetic field? B will be. Where will be my magnetic field if current is in this direction? If current is upwards, my magnetic field will be along which axis? Say if my current is along y-axis, yes, correct, Rakesh, very good. So my flux or magnetic field will be perpendicular to this, right? Yes, correct, Hariprasad. So my magnetic field will exist in this direction, B. So if then area vector will be also perpendicular to the area. So what happens? There exists. What's the angle between my magnetic field and the area vector? Guys, I want only the magnetic field and area, right? So what is the angle between magnetic field and area vector? Theta is 90 degree. Then what is cos theta? 0. Cos theta will be 0. So flux will be minimum in C. Okay, flux will be minimum in C. That's the answer. So on the basis of several experiments, Faraday observed that okay. So we'll learn about the mathematical formula for Faraday's law in the next class. Okay. Till then, guys, we'll meet back. So yeah, in yesterday's class we had learned that I think from next few classes, I mean most of the next few classes would be taken by Vishal. Okay. So there might be a chance that okay, to YouTubers, yes, I have some health issues, so I'm not able to come. I mean, I'm unable to see the. I mean, I'm unable to be in front of computer for longer time because of some irritation in my eye. So there is some problem. So my doctor has recommended not to go for longer periods of exposure to light or laptops or phones. So because of this health condition, I might have to go a bit slow. So I may go slow with your chapter. So on discussion with our manager, it was notified to me that it would be better if you could take rest. So I'll be going with 11th class from now on. So the teacher who was handling 11th class for physics would be handling your 12th from now on. So that is Vishal. So Vishal would be taking classes maybe from Monday. Yes, for you guys, yes, it would be from Monday. Or if that's being prolonged, maybe it may take some time too. I may continue for few classes, or maybe from Monday Vishal would continue. So Vishal would complete the syllabus. Yeah, he's very good. So again, he's also from Karnataka. Okay, so he will do it in a, I mean, he'll do it fast and in a better way. Okay, guys. So maybe yeah. Uh, so study well, guys. That's it. Study well and get prepared to your exams, competitive exams. Prepare well, and I'll recommend all students to write JEE mains exam, at least the first exam. So I think the first exam would be a bit easier. Okay, at least the first exam would be a bit easier. Please start your registration process for all four exams if you are willing to, or at least we recommend you guys to write at least the first exam. Okay, the very first attempt. If you are eligible, please attempt your first attempt of JEE mains, which is happening in your February. Okay, guys. Then study well. All the best for your exams. See you again later. Bye bye. Well, guys. Thank you for your cooperation. Bye bye. See you guys.